Welcome to This Explainer. Today, we're demystifying the incredible science and massive global infrastructure that powers the global positioning system. We all use that little blue dot on our screens every single day, right? But the mechanics making it happen go far, far beyond simple satellite pings. It is literally a masterclass in mathematical perfection.
Here's how we're breaking it down today. First, we'll look at the magic in your pocket, then explore why it's all about distance, not angles. After that, we'll hit the fourth satellite, which is time, look at the 3 GPS segments, and finally, figure out why GPS is sometimes inaccurate. Section 1. The magic in your pocket. Let's dive right in and look at that device sitting in the palm of your hand. So, how does your phone actually know where you are? It sounds like a super simple question, but the answer is honestly mind-bending. When you pull up a map and see that little blue dot, what invisible mechanics are working behind the scenes to pinpoint you on Earth? Most people think their phone is sending a signal up to space, asking, "Where am I?" And the satellite is talking back. But as we'll see, that is not how this works at all. Section 2. Distance, not angles. To figure out how your phone finds itself, we need to look at the geometry of navigation and bust a massive myth. You've probably heard people say GPS uses triangulation. Well, that's completely false. Triangulation is what ground surveyors use to measure unknown distances by establishing a baseline and measuring angles. GPS satellites, they don't care about angles whatsoever. Instead, they use a purely distance-based measurement method called trilateration. Think about how this builds in a 3D space. When one satellite broadcasts its signal, your receiver calculates the distance but not the direction. So that one satellite gives you a massive sphere of possible locations. A second satellite's distance intersects with the first, creating a circle of possibilities. Add a third satellite, and that intersection narrows everything down to just 2 exact points in space. So out of those 2 final points, how does your phone know which one is you? It's pretty simple logic, actually. One of those intersecting points is usually floating thousands of miles out in deep space, and the other is right here on the surface of the Earth. Your phone effortlessly eliminates the space debris option and picks the point on Earth to fix your latitude, longitude, and altitude. 3 satellites, 3 spheres, position fixed. Done, right? Section 3, the fourth satellite, time. Because, well, we aren't quite done. If 3 satellites give us our 3D position, why does the entire system mathematically demand a minimum of a 4th satellite to actually work? The secret ingredient is time. Remember, distance equals travel time multiplied by the speed of light. To measure that travel time perfectly, GPS satellites are armed with incredibly precise atomic clocks. We're talking accurate to within a single nanosecond, which are continuously synchronized with even more accurate ground clocks. But here's the catch. Your phone definitely doesn't have a multi-million-dollar atomic clock inside it. It only has a cheap quartz clock that drifts by several microseconds every single day. And when you're calculating distance based on the immense speed of light, just 1 microsecond of error translates to a massive 300-meter error in your position. Because of this unavoidable clock drift in your receiver, every single distance measurement it makes is slightly wrong by the exact same amount. Those initial spheres we talked about, they're actually the wrong size. They don't meet at a clean point. They form a messy, blurred region. This uncorrected, error-filled measurement is what we call a pseudo-range, rather than a true distance. This is where the 4th satellite acts as the ultimate mathematical plot twist. Because your receiver's clock error is identical across all measurements, it becomes a single solvable variable. You have 4 unknowns, x, y, z, and time. 3 equations can't solve for 4 unknowns, but that 4th satellite, it provides the 4th equation, turning your phone's clock error from a guessing game into exact math. Your pseudo-ranges become true ranges, and your position becomes perfectly accurate. Section 4, the 3 GPS segments. Now that we've got the math down, let's zoom out and check out the massive physical infrastructure running this whole show globally. The GPS architecture breaks down into 3 main segments. First up is the space segment, consisting of a nominal constellation of 24 operational satellites, though there are usually more, orbiting in 6 planes roughly 12,500 miles above the Earth. Next is the control segment, down on Earth, ensuring everything runs smoothly. And finally, the user segment, which includes everything from precise land surveyors to the device in your pocket. Up in that space segment, every single satellite is constantly blasting out low-power, spread-spectrum signals, primarily on the L1 and L2 frequencies. They utilize a sequence called pseudo-random noise, or PRN. To you and me, it would just sound like background static, but your receiver knows exactly how to duplicate and align this specific code to calculate the signal's travel time. But calculating distance is totally useless if you don't know exactly where the satellite was when it sent the ping. To make sense of those signals, your receiver downloads two types of hidden data tucked into the broadcast. First is the almanac data, which gives a rough estimate of where all the satellites should be. And second, the highly precise ephemeris data, which provides the exact orbital corrections and clock biases to lock onto a specific satellite's true location. Keeping that ephemeris data perfectly accurate is the job of the control segment. Because space conditions are unpredictable, solar radiation literally pushes satellites off course. The master control station in Colorado Springs constantly tracks them. They calculate precise satellite orbits and atomic clock errors, and then upload fresh ephemeris data via remote ground antennas to ensure the satellites stay exactly in position and broadcast perfectly accurate data back down to us. Section 5. Why is GPS inaccurate? Look, despite all this incredible mathematical wizardry and global synchronization, you've definitely had moments where your GPS insists you're driving your car directly into a river. So why does that happen? Well, a few key reasons. Sometimes it's due to geometric dilution of precision, which is just a fancy way of saying the satellites your phone is tracking are clustered too tightly together in the sky, magnifying errors. Other times, the signal gets delayed by the Earth's atmosphere, specifically the ionosphere or troposphere. Or, especially if you're in a city, you get multipath interference, where the signal confusingly bounces off skyscrapers before hitting your phone, tricking it into thinking the distance is longer than it actually is. If we look at a typical range error budget, the absolute biggest natural obstacle to perfect accuracy is actually the Earth's ionosphere, contributing an estimated 5 meters of error. Radiation from the sun ionizes the upper atmosphere, and that actually slows down the GPS radio signals. While modern receivers have complex math models to correct a lot of this, space weather honestly remains our biggest hurdle to precision. Understanding all of this reveals the incredible brilliance and, frankly, the fragility of our modern infrastructure. If a fraction of a microsecond of clock error can totally scramble your location on a map, consider this. What other invisible systems in our world, from global financial trading networks to telecommunications and power grids, quietly rely on the absolute perfection of GPS time to function every single day? It turns out the ultimate tool for finding our physical place in the world is, at its core, just a masterclass in keeping time.